Okay, in this last part of the transition matrix chapter, we're going to look at when we get a recurrence formula using matrices. And that's like here where you can see we still got this transition matrix that we're using, but we now get this added extra bit into the formula. So we're going to times, the transition by a state matrix, but then we're also going to, in this example, we're going to add another matrix. So we've got to be careful when we do have these recurrence relations. We always have to, you always have to find the next state by going step by step. So you always find the next state. So say e.g. S1, going step by step. So you can't use the power trick, you can't, if you want to go to S3, you have to simply keep going through them and find S1, then S2, and then S3. Okay, so let's have a look at this example here. We said a car rental starts with 90 cars, 50 located at Bendigo and 40 at Colac. So they gave you the SO and they've put that down here. And cars are usually rented and returned to the same town. However, a small percentage of cars rented in Bendigo return to Colac and vice versa. So to increase the number of cars, 2 cars are added to the fleet to reach the rental fleet at each location. So this is the extra bit B being added, and you can see the matrix B has 2 in the Bendigo spot and 2 in the Colac spot. So that's they're adding. So when they ask to determine the number of cars at each place in week 1, so really they're asking for state 1 matrix, and using that recurrence formula up here, it will be the way we find that is that you'll use the transition, you times the one before, which would be SO, and then you add B. Okay, so you can see down here I've done that. I've put the transition into my calculator, times it by SO, and I've added B. So this ends up being S1. Now to find week 2, which would be S2, the way I'm going to do it is I have to do the transition times the one before, which would be S1, and then we're going to add B. So what we do is we take the answer from S1 here, and it gets popped into the formula in there. So you can see I've done the transition times S1 plus B, and this gives me S2. So that's what I mean, you have to go step by step. You can't use any power tricks to jump to week 2. Okay, question 4. Beginning in the year 2021, a new company will take over the maintenance of the same 2,700 kilometres highway. Let M N be the state metrics that show the highway maintenance schedule after the nth year after 2020. So 2020 is going to be your MO. They're not using the letter S, they're using MO. The maintenance schedule for 2020 is shown below. So we've got, this is how we would get the next year. We're going to do the transition times the year before plus this B matrix. Okay, so it says for these 2,700 kilometres of highway, the matrix recurrence relation shown below is used to determine the number of kilometres of highway that will require each type of maintenance. Okay, so what you're asked, so you've got this recurrence relation. So here is the beginning MO, this is the transition, and here we've got this B, but we have a missing letter here, K. Now it says write down the value of K. Now what we need to know is that in this scenario, we were not losing or gaining any kilometres. So that means our answer is always got to add up to 2,700. So if you add this one up, it'll get 2,700. So if we're going to add this extra matrice, what we want to do, it needs to balance out that it doesn't, so that we don't gain any more highway. So you can see here, if we're going to minus 60 here in it, that means we need to add 60 as well. So then that would balance out to 0, so that we're essentially not adding any extra highway or value. So if we've got minus 60 and these two make up 30, then K would have to be 32, because if you total all those numbers up, it would be 0, and that's good. That means we're not adding any extra. So we can write down the value of K must be 30. And it says how many kilometres of highway are expected to be graded in the year 2022. So that would be state 2. So we've got to do the formula. So you can see here I've done the transition times MO, which was our original, plus our B, and we get this, and this would be M1, and then we put M1 down in this formula again. So this was 2021, and this is me finding 2022, and then there's plus the B, so this is M2. Now they asked for how many, so remember this is graded, resurfaced, or whatever they were, S and N, and they want how much to be graded in 2022, so we'll say 457 kilometres. Okay, the matrix Sn plus 1 is determined using this rule, so this is just how we get the next one. Given this information, S2 is equal to, so we have to get to S2, we need S1. So we can use the first one, so transition times SO minus C, and this will give S1. Okay, once we have S1, we can pop it into the formula, because this would be how we find S2. Okay, and then we get this. So the answer is S2. So we get the answer there. So essentially we're putting this answer into here, into the formula. So that's, you've got to go step by step. Okay, a series of extra rehearsals commenced in April. Each week participants could choose extra dancing rehearsals or singing rehearsals. All right, so this was all about another scenario, but we don't need all the rest of the information. We can follow it. We've obviously got this formula of how we can get the next state. So it's this is using the one, this is the one before there, and then they've got a transition, and then they've got an extra one adding on. So, and this is dancing and singing. Okay, so calculate the number of students who are expected to attend the rehearsal in week 3. Now they've said that this is L1 is week 1. So in the first week, that's first week. So L2 would be week 2 and L3. So this is me finding L2. We're using the formula. We have to use the transition times the one before, which would be L1, and then we're minusing that other matrix, and we end up with this is L2. So you can see I put L2 into the formula again, and that's so that I can find L3. So calculate the number of students who are expected to attend extra singing. So this bottom number is the singing. So we're going to say 68 students. Okay, of the students who attend extra rehearsals in week 3, how many are not expected to return for extra rehearsals in week 4? So you can see here, the total up here, when we had week 2, we had 180, and then when we go down to week 3, we've got 168. So you actually can see we're dropping by 12. But that makes sense because up here we're minusing every time 5 and 7, and 5 and 7 have 12. So if it says how many of the ones in week 3, how many in week 4, it's just going to be one of those. So we're going to see how many are not expected, and it'll be 12 students. You could have found, L4 if you wanted to and worked it out, but it will be 12 students. Okay, so they've given us a formula of how to find the next term. So we're doing transition times 1 before minus C, and they want us to find C is a column matrix. So we don't know what C is, and matrix S2 is equal to. So we've got S1, and we've been given SO, and we've got transition. So the way we would have found S1 using the formula is we would have gone the transition times the one before minus C. So if I just work out this bit on the calculator, so I would have times the transition by SO. So if I did that bit on the calculator, I will essentially get this. This is our answer. So I could say that if I keep following this down, I could say S1 is equal to, now I've done that timesing part, and I'm going to say 27, 53.3, and 22.7. And then I would have said minus this C matrix, which is a column matrix. Okay, so we're pretty much missing 3 answers in there. Okay, but we actually do know what S1 is because they told me up here. So I'm going to write that out. So S1 is actually 24, 54.3, and 20.7. And I could say it equals this 27, 53.3, and 22.7. And what happens is we minus this C matrix. If we minus this C matrix, we'll come back to this answer. So for me to go from 27 back to 3, I'd have to minus 3. Okay, so when we want to get this 53 to 54.3, so we actually want to add 1. But because this matrix is minusing, if I do minus 1 in there, it would be 3 minus... So it'd be a minus as a minus, so it becomes a plus. So that would get this 53.3 back to 54. And if I want to get this 22.7 back to 20, I just want to minus 2. So actually down here, just going to delete that, rub this out, because I've put the wrong ones in. So let's put the right ones in. So now I've worked out what this is. Essentially, I just worked out what C is, okay? So that's what C needs to be. So when we're asked to find S2, using our formula up here, they told me I need to do the transition times the one before, which would be S1, and then we've got to minus this C, which I now know is 3, -1, and 2. So we'll pop that into the calculator, and when we do that, we get 23.04, 55.78, and 16.18. Okay, so we end up with the answer A. Okay, a large population of martin birds migrate on a remote island and nest and breed. There's 4 nesting sites. Researchers suggest that the following transition can be used to predict where they nest. Question 7. 2,800 martin birds nest at Site C in 2008. Of these 2,800 martin birds, the number that nest at Site A in 2009. So we want to know when we want to go from C, nest C to nest A. So if you look up, you can look on the diagram if you like. So nest nest C to nest A is 20%. So in 2008, sitting in C, we had this 2,800 birds. So 20% of them are going to go to A. So we want 20% of 2,800. So we get 560. Question 8. The transition predicts that in the long term the mutton birds will be. So we've got the steady state. So I've done the transition to a high power there, which you can see. And I just put in, remember I said we didn't have to worry really what the state matrix is. So I've just put 100 into that, meaning like 100% of the birds. Let's see where they all divvy out. In the long run, you can see this is site A, B, C, and D. That we've only got numbers or percentages at B and C. So we can say that the birds are going to eventually only nest at B and D. Okay, now 6,000 mutton birds nest at site B in 2008. Assume equal number of birds nested at the 4 sites in 2007, and the same transition applies. The total number of mutton birds nested in the island in 2007. So the way we would find 2008 in general, so the state 2008, is we would do here. So we would do this transition times the year before, which is 2007 and 2008. So this is me writing that out there. So I've got the transition. Now it did say here that assume equal birds nested at each of the 4 sites. So I don't know what it was, but they all had the same amount. So I'm going to say let X equal the number at each site. So we would have said T transition times this 2007, which would have had the same number written in all of them. So I've called it XXX. And they did tell us that in 2008, the next year, they told us this B value. So I know it's 6,000. So it says, what's the total? We need the total number of mutton birds. So we pretty much need to know what X is so we can work out the total. So if we look at our manual multiplication, the way we found this number here was we used row 2 with column 1 and it gave us that answer. So if I wrote that out as an expression, it would have been 0.35 times X plus 1 times X plus 0.15 times X and plus 0x, and we would have said equals 6,000. So that's us knowing our manual multiplication. And because it's only got x's, you can actually solve for this. So you can go solve and we can go comma x, and we find out that x equals 4,000. So if it says what's the total number of birds in 2007, so that means we had 4,000 at each of the sites. So we'd say 4,000 times 4 equals 16,000. So D is our answer. Okay, so sometimes we have to work backwards. So I was saying if we're given our normal transition formula, so in terms of we get the next one timesing the one before, if we're actually given S3 and we've given the transition and we have to go backwards and find SO, what we can do is we can still use the power trick remember when I said that these two numbers here and here need to add up to what you want. So you can see if you go -3 plus 3, that would be 0. So if you want to go backwards, so if you're given S3 and you want to go back to SO, you can see you can just do the transition to the power of -3. So you can always, when you want to go backwards, you do negative powers. Now we have to be careful if we go backwards when we have this extra bit here. So we've got this extra value here. So if we so first of all, they're just asking us to find S2. The way we'd find S2 is you use the one before, okay? So, and we plus it. But if we want to go backwards, so say we were given here, we were given T, we were given S3, and I'm going to say we're also given C. Sorry, I probably missed that out. And you were given matrix C. If you want to go backwards, you have to go backwards in steps. So say the first thing we'd have to do, because we essentially want S2 by itself. So we want this one by itself. So the first thing I do would move this C minus matrix C. So you'll see the thing we will have, we'd have S3 and we'd add C because it went over an equal sign. And then I'd still have equals this transition times S2. Now I'm trying to get S2 by itself. So I essentially want to move this over an equal sign. Now this was timesing, so it's dividing on the other, so it means I want to times by the inverse. So I'm going to do transition to -1, and then it would be timesing what we just did here, which was S3 plus C, and then it essentially would be left with just S2 on the other side. So this would be how we go backwards. So you just got to take your do step by step. Okay, so question: a study of antelope population in wildlife parks showed that antelope regularly move between 3 locations, and we can determine where they are using this recurrence relation. Okay, so we've been given the transition and we've been given D, and we can see we get the next one using the one before. So they've said here's the state matrix A3. Now they want to know what happened in A2. So you can see A2 is the question. So I want to go backwards. So this would have been how I found A3. I would have done the transition. So over here I've got the transition times, I've put S2 there. Let's change that to A3. They're calling them A. So this is A. We would have used A2 and minus D. So what we want to do is we want to get A2 by itself. So first we'd move this D over. Now it's subtracting on this side. So when I move it over an equal sign, it actually adds. So that would be the first thing we move. And then the next thing we move is this transition matrix, because we want to get the A2 by itself. So we move that transition, and because it's timesing, we'll use the inverse on the other side. And you can see that this is essentially how we calculate A2 going backwards. So I've typed that in the calculator. Here we've got our transition to negative power times this was A3 plus D, and this ends up being my answer over here, A2. Now they just wanted what was happening at W, which was 2270. So there we go. Okay, question 8. All in an airline parks all of its planes either at Sydney Airport or Melbourne Airport. The transition below shows the change of location. Now this statement here becomes very important in the purple here. It says there are always M planes parked at Melbourne Airport. So that means that the number parked at Melbourne never change. So if the actual number never change, what goes out must come in. So if some planes go out to Sydney, Sydney must then push some planes back because the number never changes. And that was important. You needed to know that. So there were always S planes parked at Sydney, and they're saying the same thing there. So what goes out of Sydney must go in. So of the planes parked at Melbourne Airport on Tuesday night, 12 had been parked at Sydney on Monday night. So when we went from state to state, in here, we were talking about going from Sydney going to Melbourne, and they said 12 went out. So of the ones parked in Melbourne, 12 had been at Sydney. So from Sydney to Melbourne, it was 12. So here I know when we say Sydney, when we go from Sydney to Melbourne, it says that it's 0.48. So you know that Sydney times the Sydney amount would be 12. So there's that. So we end up finding, and we know that Sydney, we can calculate, therefore, if 12 equals 48% of the Sydney, so this is how we find it. So Sydney's got 25. But then because of the fact we said what goes out must go in, we then knew that 12, if 12 came into Melbourne, 12 went out of Melbourne. So this is where I've gone, all right, so from Melbourne to Sydney, 12 went out. And that indicated when you go from Melbourne to Sydney, it was 0.2. So Melbourne times 0.2 also equaled 12. So we end up finding what Melbourne is, and then you add them together to get the total, which was 85, which is the answer. It was a pretty hard question. It's important to read all the information. Okay, so 10,000 trout eggs, 1,000 baby trout, and 800 adult are added to a pond. They can either die, the eggs can die or become baby trout, and baby trout can die or become an adult trout. And they've got to transition to set up this, how they work. Use the information transition matrix to determine the number of eggs in this population that die in the first year. So what you're looking for is your egg this year, but you died next year. So that would be 0.6. So we're saying 0.6 of the eggs, which was 10,000, they died in the first year. So you just go 0.6 times 10,000, which equals 600 eggs. Okay, and then it says complete the diagram showing the relevant percentages. So if I go, and I'm just going to look at A for the moment, A this year, now A next year is 0.5. So that means I would have a circle around like that, and they're changing it to percentages, so I'll do percentage. And we also have, if you're A this year, 0.5, you go to 0.5 go to D. So I'm going to do A to D like that, is also 50%. Okay, let's have a look at all the rest of it. D, now we have D. If you're at D this year and you're still dead next year, so once you're at D, you're 100% going back to D. And is there anything from B to A? We can see that too. So if you're B this year, 25% at A next year. So B go to adults, 25%. And B to D, we're also missing. B to D. So this B this year, you're dead next year, would be 75%, like that. And all the rest, hopefully, have been drawn on. So the purple one was there, E to D, and we've also got E to B. So we've covered them all. Okay, the next part of the question, it says the initial state matrix is there, so we already worked that out, but that's good. And then it says the rule can be found. Now this is just an old exam, so they wrote it like this, but we're used to writing it like that, and it just means how you get the next one. So it's pretty much meaning you use a transition times the one before. So they want you to find state 1. So I've done that there. So you'd be writing this out as your answer. Just did the transition times SO. Okay, and the number of adult trout predicted to be in the population after 4 years. So we're going to do the transition to the power of 4 times SO, and we get the answer. So this would be S4, and they want the number of adults, which is this one down here. So we're just going to round that to a whole number, and would say 3, 3, 1. Okay, the transition matrix predicts that in the long term all the eggs and baby trout and adult trout will die. How many years will it take for the adult trout to die? That is, when is the number less than 1? So I'm just doing the transition. So I tried power of 10 because we were already up to 4. So we did a power of 10. Here's my adult. We're still at 5. So I did 11. When I did 11, I'm still at 2.5. I did at 12, I got 1. And when I did power of 13, I ended up with it's less than 1. So it's now less than 1. So how many years? Because it was a power of 13. And I say 13 years. So you just have to keep trying step by step. So it reached the long term pretty quick. What is the largest number of adult trout predicted in the pond in any 1 year? So you have to be careful here. We'd already seen the initial state S1, and we saw that adult was 650. If you actually did S2, you actually see that the adults go up because the babies grow up. So we see the babies go here, but we're now dropping off. We've got no more babies to grow. So then we start to die off. So when we go to year 3, we can see the numbers dropping. So it was, what is the largest number of adult trout predicted? So it was actually in year 2, and it's 1325. Just have to be careful that it was probably not as, some people probably just wrote the beginning one, 800, but remember the babies could grow up, so you might have had to have a look, and it's trial by error, have a look. Determine the number of eggs, question D, number of eggs, baby trout and adult trout, that if added to or removed from the pond each year will ensure the number of eggs and baby trout in the population remain constant. So if this is what we had in the beginning, and if you do the transition once and we go to S1, we can see we have 0 eggs, then we have 4,000 babies, 650 adults and thing. So what we want to do is, it's like, what can we add to get it back to this? So we're looking at S1, so to get it back to that, I'd have to add 10,000 more eggs. Now, we had 4,000, we've got 4,000 babies, but we want to go back to 1,000. So I'm going to minus 3,000. And adults, we're at 650, we need 800. So we'll add 150 adults. And we had the deaths, so we want to get that back to 0. So that's this would be what we need to do to go back to this, which is the initial state, which is what they're asking us. So we just have to write out what we need to do. We determine the number of eggs. We need to add 10,000 eggs. So that was that first one. The second one was babies. So we need to subtract 3,000 babies. 3,000 baby trout. Then we need to add 150 adult trout. And take away the 7,150 dead trout. Okay, so you're just pretty much writing out what you worked out. Okay, this question continued, and we got this new formula for the population of trout in the thing. Now you can see here in this formula, you're actually using the one before twice, and that's okay. You just pop in the formula. You also have another matrix in there, M, and we're just going to put that in. They've given you M here, and you'd use the one before. So here when they ask you to determine S1, you just have to follow the formula. So I have to use the transition, which they gave me. So I've got the transition, which is here, then the rule says times it by SO, so I've times it by SO. Then you're going to add 500, so I've done that, add 500 times M, so I've typed in matrix M, and then timesing by the SO again, so I've typed in that same matrix. Now that will give you S1, so it doesn't matter if it's got whatever it's got in the formula, just follow the formula. So this is S1, so this was the answer to I. And then this pattern continues, so the matrix describing the population can be used like that. So don't worry, it's just the same. Use this rule to determine the population after 2 years. So they just want you to keep going. So you've found S1, so that means you'd pop S1 into that formula again, obviously twice, and then you find it. So we just type that in and we get S2, the answer. Don't worry, this is just old school. You would probably see it written like this. They'll write yours with using like that. It means the same thing. Okay, a market research study of shoppers showed that buying preferences for 3 olive oils, C, L and O, changed from month to month, and there's your transition. Then they gave you what everyone initially bought, and they said July was SO. And it says less SN equal the number of olive oils each brand after months in July. So how many of the 8,000 shoppers bought a different brand of olive oil in August? So August would be state 1 because July was SO. So if you change brands, you can see up here I've highlighted. If you were C to begin with, it's going to be all the 2 options where you don't go back to yourself. So up here, when I'm looking at the C brand, you can see I've got 0.5% go to the L and 10% go to the O. So in total, that would be 15%, and that's what I've said. So 15% of the C change. Then if you look at the L, some change to C and some change to O, and both are 10%. So 10 plus 10 is 20. So 20% of the L change. And then if you look at the O brand and what went to different things, it's the C and L. So it's 5% and 5%. So 10% in total. So what we're going to do is we're saying 15% of the C changed, and we just use the C value, which is 3,200 and so on, and we find it out over here. So we find out all those numbers and we add it up. So of all these customers, how many changed, and we just would write the answer there of 1160. Okay, it then says use the rule and find S1. So I've just done transition times that SO, and I get S1, and it's good I got the first answer, and I just fill in those missing pieces. Now it says consider the shoppers who expected to buy C oil in August. So we're looking in August, so remember this is CLO. So in August, there was 3,060 of the C brand. So what percentage of these ones? So when we do a percentage, we do the total. So they're talking about the total. So you can see down here in the purple, I've put that total. Now, what percentage of them had also bought the C in July? So if you look up, if you're going from C to C, it's 0.85. So in July, we had 3,200, so it's 0.85% of them, of that. So I find the 270 and I put it in, and this is how I get the percentage. Okay, write down a calculation that shows that O olive brand is the brand bought by 50% of the shoppers in long run. So in the long run, we need the transition to high power times SO. So we found that, and you can see that O rounds up to 4,000. So if you've got 4,000 in the long run, now there's still 8,000 customers. So 4,000 out of 8,000 times 100 is 50%. So you probably had to show this to get the 1 mark. But obviously we needed to do it on the calc to work out. So further suggests, so here you can see they'll set up a new recurrence relation of how you get the next term. So it's a little bit blurry here, but they're calling it R this time. So you do the transition times the one before plus this matrix B. Okay, that's the new formula written here. Okay, and now we can see that K is missing. They've given us RO, so it represents, K represents the extra number of shoppers expected to buy olive oil each month. So what we need to do, now they've given us R2. Okay, so K represents extra shoppers. So this B thing, we're adding extra shoppers to every time we do this transition thing. So what we're going to do, we have a look and we're missing K, but they said R2. So R2 means we would have gone, we've got RO here, we would have gone through the process twice. So this B would have been added on twice when we get there. So I'm showing you that here. So if you have B plus B, you would have had these 200, 200 plus a K and a K. So we ended up with, we would have had this much extra, so 600 plus 2K. Now we can see if you add this up, this was 8,000 to begin with. And when we get to R2, we're at 9,000. So over 2 years, there's been an extra 1,000. So I'm saying that if you add all these up, it's got to equal extra 1,000, and we can solve and find K. So we end up with K is 200. It's just a hard question. Hopefully with an example, you can work out your one that you get.